Good afternoon, folks, or good morning, perhaps. My name is Michael Wenzel. I'm a professor at Augsburg University in Minneapolis, Minnesota. And I've partnered with a couple of folks, Jane and Monica, and a couple of folks from Omnitech. We were supported by the U.S. Soybean Board and also with Beyond Benign to develop curriculum materials based on soybean chemistry and how it's innovative and how it addresses green chemistry and sustainability goals. And so that was kind of our objective to bring this really new, cool, and interesting chemistry that's relevant that maybe folks might not know about and bring it to students. So we developed three modules. So the goal today is kind of give you a flavor of some of the case studies we have, a little bit of background, a little bit about the case studies, but then we'll have breakout rooms to really get to the nitty-gritty details and see how folks can implement these things in their classrooms. Um, so the modules contain documents, PowerPoint slides, some have videos, student activities and assessments, just some guides, nothing that's rigid by any means, but something we want to use. So curriculum overview. So what we're going to use, this is tailored to higher education, but I think it could be possible for a higher level high school class. We want to make it flexible. We want people to use these. So we want to make them as flexible as possible, but also as useful as possible for folks to meet some of these different standards that we have for ACS accreditation or for high school standards. So what we have, the three modules. The first one's more of a background in history. The second one's the case studies, which we'll kind of highlight today a little bit more. And then the third one's actually a lab experiment that folks will be able to do too. We have the learning outcomes. It shows emerging innovations, really cutting edge things that are going on using chemistry within the soybean industry. Yeah, so we're going to again highlight case studies. So one of the first ones, so I got my thing is, I gotta, oh, I miss using Zoom. I gotta get rid of that. Okay. So different emerging technologies. So this is a list of the soybean, the green chemistry modules we have. So there's six of them here, and we will kind of talk through a couple of them. You notice how we have kind of highlighting the major aspect of what's going on with each one as far as wood adhesives, candles, or foams, transformations, asphalts as well. So like we said, the target audience for these high school educators, higher level or higher education, we really wanted to make it so this is maybe a scaffolded type thing, kind of depending on how the instructor wants to use the materials. It could be for a general chemistry to organic to more of a specialized materials or polymers class even. And we really wanted it to have it be context based, right? As well to inspire students for these kind of real world applications. And of course, this would also help ACS programs with the new guidelines from 2023 to include green chemistry and sustainability coursework, as well as systems thinking too. So student learning outcomes, I think this is a soybean is a good kind of model system to show a lot of different cool chemistry and how chemists can be creative and do different things. So we wanted to identify the key parts of the soybean oil or soybean and the oil and things of that nature and how different reactions, like reactions they learn in class, but they're being used on an actual commodity that's on a large scale here in the United States and other places. Um, they wanted to how they can replace, right? How this sustainable material, this sustainable resource can replace some of the other petroleum-based non-renewable sources. Then also explain how they can use green chemistry and sustainable applications in these case studies. They're also, these modules 2B are kind of different as well, done by Julian Silverman. These also use life cycle analysis and techno-economic assessment tools to evaluate products that are being commercialized. So I think, again, it's kind of a neat example of systems thinking, right? As scientists, as chemists, you have to also be thinking not just about getting your product, getting your yield, but what is applying outward? What are the other systems being involved with your work? So those are a neat example that maybe a chemist hasn't been exposed to a lot, or students for sure. All right, Jane.
All right, hello everybody. I'm Jane Wissinger, Professor Emerita from the University of Minnesota. I was the Organic Laboratory and Director and taught organic chemistry and green chemistry there. But now, in my retirement, I'm enjoying doing a lot of extra green and sustainable chemistry initiatives through ACS and IUPAC. So I was really excited about joining this project. I've worked a lot in the area of corn and plastics. So what can you do with soybeans? And so first of all, we did create the module one that gives everybody the background of, well, where's the oil or the meal come from in the soybean? So soybean oil is about 20% of a bean that you harvest. The meal's the other part. And they each have their different chemistries that we wanted to parse out. And those chemistries are very different, and their applications for industry are different too. Certainly, the oil is a little more developed. And so we have a lot of representations there. And I knew triglycerides were in the oil, like other oil seed materials, but this really hones in on what you can do with soybean oil. And here's just an example of the triglycerides. And so when you're thinking of placing in your curriculum, you can see we have the ester bonds. Of course, many people make biodiesel, but there's a lot of other chemistry that can be looked at with your students and for really neat applications. So they can look at the structure property relationships based on the fatty acid chains, the reactions that can happen with the double bonds, noting they're mostly cis double bonds, and then the products from that. For example, epoxidized soybean oil is used a lot in industry. And then we get into with the case studies what applications you can use. For the meal, whoops, okay, there are both carbohydrates and protein structures. This is more complex, but again, replacements for different applications that we have that are based on fossil fuels are being innovative and derived from the meal that introduce additives that are less toxic, biodegradable, etc. So the green and sustainable chemistry is there for wood adhesives, paper coatings, etc. So that is kind of the overview of what all of the curriculum is about. So let's look at two case studies, two of the seven, and just show you what we hope educators think will be a great start for their classrooms. The first one is one of the very early initiatives of using soybean. Besides, of course, soybean, the history is fascinating. I mean, it's like from BC in China, and the history is fascinating. So I hope you have an opportunity to take a look at that. But it in moving from food and agriculture, forage for animals and animal feeds. The oil has now found many, many uses in industry. And the one I'm showing here is a Presidential Green Chemistry Challenge Award from 2019. And so for each module, we talk about the chemistry concepts that are embedded and then what courses they might align with. And so electrical transformers was the center of this innovation. And I really like this case study because there's a lot of dimensions to it. So transformers are everywhere around the world. It relates to everybody. You can look outside your window somewhere and see a transformer. And what transformers need is an insulant and coolant liquid. So the original was based on petroleum, of course. It was mineral oil, but mineral oil is very flammable, and there was a lot of fires based on mineral oil. And then contamination from the mineral oil that spilled. So chemists got busy and said, how can we make a different material? And they came up with polychlorinated biphenyls. And so demonstrates a really good example of, yes, we solved one problem. We solved for function, a less flammable material, But we all know now that PCBs are persistent organic pollutants that are, contaminating air, water, and soil. So they have been banned. All right, so this is an example of a regrettable substitution that you can bring to students and really demonstrate the power of systems thinking. So the reduction of approach of just like, well, let's solve the flammability problem, of course. Come on, so slow. Keep up with me. The unintended consequences. And with systems thinking, you would consider all the different aspects. What happens if there's a spill? Um, what could be a circular economy using a renewable material? And so using systems thinking is can be incorporated in this module. And this reference is a really nice, by Paul Anastas, is a really short introduction to systems thinking, but there's lots of resources there these days. So again, the chemistry that you can talk about is of the soybean oil. I'm not going to go over all this, but talking about the double bonds and cis trans and reactivity and toxicity, etc. And with each module, we would provide student activities to incorporate the chemistry. So getting to the points of the whole case study is that soybeans came to the rescue here. That is, Cargill Incorporated designed a soybean oil that is now used in many, many transformers. That we present the chemistry of the different properties that improve its performance over mineral oil and the PCBs. So it can operate at higher temperatures, better capacity. Zero fires have been reported using this new product by Cargill that's based on soybeans, and it's biodegradable in the environment. Win-win here. So, sorry. On to Michael.
All right.
Tell us
So
about wood adhesives.
yeah, so another one of the case studies that we worked on developing was about wood adhesives and how we've used soybeans for that. Can you go back one more, Jane? Or you're moving me on?
Oh, I'm sorry. I'm
You're
sorry.
okay. Yeah, and so um, how do we put again another idea for a replacement of a petroleum-based adhesive? One of the things I think as chemists, maybe industrial chemists knows more, but there's a lot of chemistry and materials, obviously, but also adhesives. We don't think a lot about adhesives, and they're very present in our everyday life in lots of different ways. And one of these examples is wood adhesives. So using the soy flour chemistry are based in innovations to replace some of those petroleum-based things, and a lot of learning about the protein structure and hierarchy, and then also some polymer chemistry built in there too. So now we can go ahead to the next one, Jane. Right, so here are the examples of the petroleum-based wood adhesives that have been used. So urea formaldehyde, polymethylene, diphenyl diisocyanate. So these are common ones current or had been used or currently used. But these things obviously have some issues. Different amount, they're gases, they're different hazards for that way. And health hazards for folks actually trying to build these materials or doing the manufacturing. So an alternative was needed here. There we go again. Doubled up. So this is kind of neat to think about that the chemistry of the soy protein, right? They can actually see all four levels of the protein structure hierarchy are present here. So you can imagine, maybe not as an organic class, but in organic or maybe in a biochemistry type class, this could be an interesting piece to really think about, the structures, right? The protein structures of these proteins. They're larger, they're smaller proteins versus peptides. There's crystal structures that you can look at to think about the different dominant proteins, obviously. The folding, again, thinking about the hierarchical structure of proteins in all four levels. And then actually thinking about not only obviously the protein structure and those things, because now we're going to show some things that make me feel more comfortable and happy. Actually, not the cartoon drawings, we're going to actually see some bonds being made and broken here. So Jane's going to show that. There, oh, good, there they are. There's the organic molecules. Now we've gone into organic chemistry. But so how this actually works to replace these pieces, this is known as polyamide epichlorohydrin. Um, so again, known for its wet strength. So you can see some nice uh, condensation type chemistry here. You can also see some obviously polymerization through those polycondensations there, and also some interesting substitution reactions where you actually make some four-membered rings from these epichlorohydrins. So the neat part here, right, and I think this is actually a fun thing I always talk to my students about. Perhaps I always, our bodies are chock full of nucleophiles. And so like a lot of proteins, a lot of nitrogen sitting around, and soy protein is similar. And so there's nitrogens around, there's nucleophilic parts. And that four-membered ring, we actually see those four-membered rings in a lot of classic kind of drug type molecules. So it's a neat thing to show them that as well, that this kind of substitution is seen in nature for bioactive molecules too. And so this cross-linking occurs from opening that four-membered ring. Is a nice way for them to show that. And again, the benefits is a wildly abundant thing that's cost effective, non-toxic, renewable, and then doesn't have the volatile organic chemistry profile as well. So, to kind of sum things up, in these case studies, we also want to try to bring it back home to grounding it in within the principles of green chemistry and kind of highlighting where those things are being shown. So obviously renewable feedstock, right? So supporting agriculture, lower volatile organic emissions, right? Now the formaldehyde for the people actually building these things or manufacturing these things, biodegradable, right? Naturally decomposes is soybean flour, soybean proteins. And then carbon reduction, right? Reducing the greenhouse gases as well. So it's a nice way to anchor these things back into the 12 principles of green chemistry as well. And for each of these case studies, we just want to highlight this here that we do have different activities and discussion points. These are not, we want this to be not restrictive, but also a point of ideas generation, to have some ideas that we've done some of these things. So again, so if we drop in, but obviously they're easily adaptable as well. But we wanted to show that we had some of these different ideas, points to discuss that we thought would be appropriate with what we were talking about in each of the modules. You're muted, Jane.
All right. I'm not in my usual workstation, so it's confusing. Okay, so that's kind of the overview of the case of two of the seven case studies that we built, and some select things. There's some about candle wax and what else? Oh, asphalt. When the soy people talked about asphalt, it's like, oh my gosh, asphalt seems pretty boring, but it's not. There's so many cool applications of soy. And when I started looking in like some of the products that was used, like fingernail, I got little stick-on fingernails for my granddaughters. I'm like, oh, it says there's soy in this, soy oil. So start taking a look. But what we want to do now is have breakout rooms to see of the case studies that we presented, and I believe they're on this slide, to have a discussion of where you might see this would fit into your curriculum. And so identify what course or courses you would consider implementing and what level that is. In what context would you introduce it as a way to introduce green and sustainable chemistry? Would you use it to introduce organic chemistry concepts and reactions? So have a discussion in your group about that. And then, can't see my other question here. Of course, what we understand with all of this is we're all stretched with time, or have time constraints. Where could you replace it? Where could you put it in your curriculum so that you still would meet your student learning goals? So that is our task now. And Monica has made three,
Yes, two.
two rooms
Yeah, you should be able
that
to
we
join.
would ask each of you to join. I'll join one, Michael, you can join two, and we can have a discussion.